a different time for you. So let me start by welcoming you to the second webinar on simple mixtures analysis. I spoke to you about 2 weeks ago in a broader sense, and I'll be reviewing some of that material before I delve into the detail that constitutes the second webinar. So the idea here is that we're going to move from what we spoke about in the first one, which was largely around usability and general themes about the software, and now delve into the specifics of how you would actually set it up largely for yourself, for your particular analysis. So I will start with reviewing a few slides from last time, just to get everyone on page, and so that you can see this on its own and it makes some sense. So let's dive in. We've got quite a bit to get through today. I'll go through this early stuff which relates to the first webinar, as I said, and then I'll go through some PowerPoint slides that show you a lot of what has to do with the SMA setup for particular experiments, and then I'll give you some examples so you'll get a rounded view today. Okay, I may just leave it at that for now because that's working strangely. Okay, so for a recap of the first webinar, we looked at some fundamentals of quantitation using NMR and mixed analysis by NMR. We considered largely targeted analysis in this particular case, and we considered ways in which targeted analysis can be extended through different experiments. And in the context of the analysis, we are looking today at SMA, Simple Mixtures Analysis, which is a plugin provided by Mestrolab. And the things that make this unique are the fact that it's an open architecture which allows you to design and deploy your own experiments. So as such, it's fully customizable for any quantitation analysis. It provides a flexible workflow, which we discussed in detail in the first webinar, and it has, in addition to the user interface, to the interactive mode, it has also batch and real-time processing capabilities. And I showed some examples of how you can use it to determine purity, look at edible oil composition, and look at metabolites in a tissue extract. So if we think about targeted analysis and NMR, what we need to know is that a unique component in the mixture is identified by one or more peaks, a multiplet or spectral range, and the area of that is divided by the number of nuclides is this fundamental property called this normalized area, or absolute area divided by number of nuclides. It's got a number of terms, but if you look around in the quantification literature, you'll see this referred to all the time. It's really the fundamental unit. So what we need to do, what we need is fundamentally a formula that's going to convert this AI over NN into some sort of quantitation unit. And there are many formulae that can be applied depending on the analysis result that you're looking for. So the most fundamental of these is the determination of concentration, which says basically that the concentration of a component is proportional to this AI of NN for all species in the mixture. And the proportionality constant here is spectrometer dependent and experimentally dependent, and that can be determined and used in this particular equation for concentration determination. Okay, so the QNMR equations are there's not a lot of them that you really need to worry about or might consider using, but here are a couple that you may find useful. So some sort of mole ratio might be given by this particular equation here. These are all textbook equations. There's nothing particularly fancy over here. And what I've done in each case is to show you the the equation, then I'm showing you the SMA equation that corresponds to that. And this will make a lot more sense as we progress through the webinar today. So don't worry too much about this column here, the SMA equation. We'll spend a lot of time talking about that later. And so you can specify any equation really. It doesn't have to be a particular one for QNMR. It can be empirically derived or anything you like really. So this design and deploy philosophy is one where experiments are very easily performed, and the fundamental unit here is something of a library, if you like. So we have a library of experiments which allows us to share those experiments, and each experiment is a specific analysis. And within the NMR SMA software, you specify exactly how the extracted data is tailored to your specific QNMR tasks. So you can extract the signal and the spectral region areas, and then you can use a mathematical expression to convert that area into some sort of concentration or QNMR unit that's useful to you. And this is what we're going to be focusing on today, this whole business of libraries and specific analyses and how to set up these analyses. Okay, so what we're going to talk about today, this is the agenda for today's webinar, Webinar 2. We're going to talk about the way in which you can manage your experiments in libraries, how this is done, very easy, how you can create your own experiments using standard input or integrating with your database, Mnova database, should you have that. I'll describe to you this peak pattern recognition, PPR capability. It's not in full production at the moment, so I'll show you a quite simple example of that. I'll show you how you can use statistics as well within your analysis. So I'll also give a little demo of batch and real-time analysis. Batch, actually. And then I'll talk a little bit about what's on the immediate horizon in terms of the upcoming version of SMA, which will be version 1.1. And this has significant improvements. And I'm not going to talk a huge amount about it, but whenever you see this cherry little sun here with 1.1 in it on a slide, that means that the material that I'm discussing in that slide will be enhanced in the newer version. Okay. Right, so library management. First topic of the day. We have this library, and the idea here is the paradigm is simply that you have a directory, and within that directory you have experiments. Okay, so these are the experiments, and these are listed over here, and next to each of these is a little description, and you'll see this in a second, that we can add a new experiment by clicking on the plus button there and delete them with the minus button. So that's all okay, and what this corresponds to very simply is a folder on your disk drive or somewhere on some sort of virtual drive somewhere, if you like. And within each of these, within this folder is a series of EXP files. So you can see the aloe vera here corresponds to that one over there. And each of these is just a little file which can in fact be shared, and this is the essence of sharing experiments. Okay, so it's simply these files here that can be shared between you and your colleagues if you want to. Now we're going to be going through a lot of information about the experiment in the next few minutes, and I'm going to keep on drilling down and down and down into the detail, and then finally I'll show you a demonstration of how to actually set this up for a simple experiment. Okay, so anatomy of an experiment. In the first top bit over here, you simply put the name of the experiment and a short description, and the units that you'll be calculating. So this doesn't have any real meaning. It's really just a little bit of text there that you can use to make your reports look correct. In this region over here, the central region over here, is where we'll list each of the components that we'll be analyzing for, and these can be switched off and on for analysis, and these can be saved and retrieved and so on and so forth. It's pretty obvious what that is. And the meat of this all is the bit down at the bottom here. So when you click on one of the compounds in the middle section, and what you get is the detail that pertains to that particular compound. So here are the details in this bottom section. Okay, so the component details appear in a little window that looks like this. So we're drilling down a little bit now in information. This is the bottom region of the slide I showed you a second ago. And what you can see here is a section here with general information in the top over here. You can see an area where you can select the integration method, how you would like the integrations to be determined for your components. You'll see a formula region over here, so this will be displayed in the formula editor, and clicking on the pencil opens the formula editor. And then on the right hand side here we have the ppm ranges, various ways in which to import them, which you'll see in a minute. Okay, and lastly, this is quite an important button. Once you've filled in all the information over here, when you are ready to add that to the table for the first time, you must click on that button over there. Otherwise, you stand to possibly lose your data and have to put it all in again. So don't forget that add to table button. Right, let's drill down a little bit now and look at the sections of the window that I just showed you. So this is the general information section. So the first of these is to say for the particular component of the mixture, whether this will be derived from a 1D or a 2D spectrum. Okay, so this purely affects the way in which the ranges are shown to you. So 1D or 2D in the pull-down menu. The second of these is to say which of the experiments to use. If you recall, SMA has the capability of using data from multiple experiments. So if you have 4 experiments in your particular document, 4 pages, you can specifically go to data from any of those. So I'm specifying that I'm using data from page 1 here. Molecular weight can be added here, and that can then be referenced from the formula editor, and it's called MW. And fifthly, number 4, this is where we can put valid limits. So this is a bit like your blood cholesterol. Certain limits are considered healthy, and you can do this here as well. So you can say, you can set bounds here, and if the result falls outside of those bounds, then the result will be shown in red in the table. Okay, and lastly, you have the compound type, and there's only one that's reserved word, and that's a reference. So if you use the word reference here, that has a special meaning, which you'll see in a second. But you can put any other type there that you wish, so metabolite, or in this case, or component, or solvent, or whatever you like there. That's purely up to you. Right, so let's look at these ppm ranges. So you can specify 0 or more ranges. Generally, you're going to have at least 1, I guess. And when you specify these, the minimum you need to do is to specify the to and from range, if you like, and usually the number of nuclides. Now, the multiplicity and the J's and so on and so forth are optional. You can set them if you wish. And if you do so, then you can have access to the alerts. So if you say, well, I'm expecting a J of 7 Hertz, and it finds a J of 9 Hertz, then an alert will be shown and say the wrong J is found, and then you can go and look and see why that's a problem. And you can set the thresholds for these alerts, and you can set whether or not they are checked. The other things on this that are noteworthy, the fact that you've got various input methods. You've got manual input, so you simply type in the numbers. You've got 2 quick import capabilities. One from a database. If you look at the name of the compound and you click on the database button, then that will be, the database will be searched, and if that is found, then that compound name is found, then the ranges from the database will be imported, and the same holds from a Mnova file. There's one button that's a little bit special, and this one over here, number 5, which lets you go off and select an Mnova file, which then is used for the peak pattern recognition algorithm. Okay, and in that case, you don't see ranges and so on. You just see a reference to the spectrum. Okay, let's talk a little bit about integration methods. This is quite a big subject, really, so I'll gloss over this fairly quickly and allow you to read what's on here at your leisure. So we support 3 ways in which to integrate regions of the spectrum. The first of these is using GSD peaks. So if you select peaks in this particular region of the panel, this will use GSD peak areas that it derives. This is generally used when spectra are relatively complicated, and this gives you an accuracy of something of the order of probably about 2% or so, probably not better than that. Now the sum integral is the classical integration method that everyone's used for years and years and years, and is appropriate to use when you have relatively simple spectra with little overlap. So it's simply going to determine the area from one ppm value to a second ppm value, and it gives you good, much better accuracy, really, and you can expect that to be something of the order of about 0.5% or so. Now, the last of these is the edited sum, which is a special algorithm that we have developed with input from Torsten Schönberger. And this is very much related to the sum integration, but it allows for manual editing. So it allows you to remove a peak from an area, if you like. And this is appropriate when the highest precision is needed, and this allows you to go down below the 0.5% accuracy level. So we have a presentation on that available if you'd like to see a little bit more about that, and we'll certainly publish and say a bit more about that. Okay, so the formula editor now. As I mentioned, there's something special called the reference. When the type is referenced, then what you'll see is a little notice here that says this formula determines the CCF. So this is the formula editor pane, and I'll talk about this in detail in the following slides. But I just wanted to draw your attention to the fact that when the type is referenced, then you will see this, and what this means is that the particular formula that you apply over here is used to, well, the value of that enumerated formula is put into the value called CCF, which you can use later. Okay, so this is the way, and CCF is the proportionality constant that's used for concentration determination. So this equation that you see over here is simply something of a reversal, of a rearrangement, if you like, of the equation I showed you on an earlier slide of concentration equals CCF times AI over double N. Okay, so that's over there. So when the compound type is anything else, you'll get a window that looks a bit like this, if you like. And here again, I've simply put out the concentration formula here. Okay, so we'll look at this in more detail soon. So the formula says one formula per compound. You can't have more than one. You can use terms which are specified in the legends, which I'll show you in a second. The specific values for the compound will be substituted in the equation. So, for example, if you ask for an integral for region number 1, then when you actually do the analysis, then that integral will be fetched from the spectrum and put into that variable I1. Okay. You have access to common maths functions, and you have an ability to check your formula before you commit it. Math functions are many and varied. I think the two that I like the most are the power one here and the square root one, because these are used to determine standard deviations. The rest I haven't used personally, to be honest, but they're there. Okay, so let's look at these. Let's look at the formula editor, and I mentioned that there's a whole bunch of things that you can use within the formula, and these are the I1s and NN1s and so on and so forth. And this may seem daunting at first, but they're always listed in this legend section of the formula editor. So if I click on the integrals tab over here, it'll show me that I1 is this region from 7.95 to 8. IR1 is that region over there, and there's a little bit of further information down below that. If I'm interested in the number of nuclides, those are the way in which I can use them in the equations. I can use NN1 or NNR1, and they will correspond to those. The third of these is a bunch of other things which can be collected. Normally, these are normally mentioned on the compound-specific, the sample-specific data. So the sample weight and the reference weight, dilution, and so on. Molecular weight comes from the compound itself. So these are other things that you can use. And lastly, and this is an important one, you can use data that relate to analyses that have been performed previously in this particular experiment. This sounds a bit weird. So what this is saying is that I've done a number of other determinations, and below that I can access the results of those determinations. Okay, you'll see this in a second, and hopefully it'll be clearer to you. But here it's saying that there was an analysis performed called 002 underscore ascorbic acid, and I can access the result of that concentration determination by using C underscore blah de blah, and I can put that into an equation. You'll see that in the example. Okay, I spoke about alerts and how you can turn them on or turn them off. These are over here. So we've been looking previously at the compound tab, and this is right next to it is the alerts tab, and this allows you to check off and on for the particular compound whether or not it's going to look at the relative areas ratio. So if you have two multiplets, one with the area number of nuclides 2, one with the number of nuclides 3, it'll look to see that the ratio of those two is approximately 0.6. And if it isn't within, then it'll throw an alert. You can check the J's, multiplicity, so on and so forth, or you can turn them off and just ignore them. Ask the program to ignore them. Okay, here again, the same equations, set of equations, and this is just to say that we're going to be looking at an example now of looking at a mole ratio. So we're going to be looking at this type of scenario over here. So it's simply the integral of compound X divided by compound Y times the number of nuclides for X, for Y divided by that for X, and this is how it's going to look, something similar to that in the formula editor within SMA. So let's do some demos now. Get my notes out here. Okay, right, so I'm going to switch from PowerPoint to Mnova. Okay, so what we're doing in this first example is to look at a spectrum of a mixture of brucine that's been spiked with a little bit of diethyl ether. So these are the signals for the ether on the top in blue, and this is the spectrum of the mixture at the bottom. So you can see quite clearly the triplet and the quartet for 6 and 4 protons from ether. This is just to show you what we're doing. It's obviously quite a simple example, but the idea is to show you how it works. So we're actually going to be working with the single spectrum on its own over here for the analysis. Okay, so let's start up SMA, and create the experiment. Okay, so if we go to the libraries, we can see all of that there, and I need to add a new experiment. Okay, add item, and I get this blank canvas over here for me to fill in, and I've got to fill in the whole lot. That'll be it. So let's go here, webinar 2, test 2, something like this. So mole percent ether in brucine, something like that, and the units are fine. I'll leave it at that. So we need to start adding compounds. Now, I think I told you that in every experiment you need a reference whether or not you're actually going to use it. Okay, so I don't actually need a reference, but I need to mention it. So I'm going to call something ref. I'm not actually going to specify even a range, but in this case, and in the formula editor, I'm just going to put the value of 1. So clicking on that pops up the formula editor. I'm putting the value of 1 in it, and the integration method is irrelevant because it's not using anything here at all. Remember to hit the Add New Compound button, yeah? There we go. So you can see that's been added to the table now. And so that's our dummy reference, if you like. So this may sound a bit pedantic, but this can be quite a nice place to store constants. So even if you're not using a CCF value, and you had some sort of constant that you're using through a lot of your experiments, you could hide the value in here. Okay, so let's add to that. Let's add the brucine. So we can just edit this. So brucine is compound. It has, I don't need the molecular weight, but if I were to work out the weight percentage, then I certainly would. So I may as well put it in. So I'm looking at the sum integral, and I'm going to add a range. I'm going to do this manually in this case. So I'm going to do it I'm going to pick out one of the aromatics. It's actually a singlet. And okay, so I've got the compound, I've given it a color. I've called it compound. I don't need to worry about limits. I'm going to use sum integral for it, and I'm going to integrate over this ppm range over here. And the last thing to do is to specify the formula. So let's open the formula editor, and we can see that we've got available I1 and NN1, and that's all I'm going to do. I1 over NN1. That's the one that we do frequently, yeah? Check the formula. Yes, okay, that's fine. So I'll click on OK. That'll be put in there. And I'm ready now to add brucine to my list. Okay, so click on the Add New Compound button, and in it goes, brucine. Okay? Right, so now I need to do ether. So let's start with that. So, diethyl ether, its molecular weight is 74.12. Now that's not its range, so I'm going to remove that. Okay, so this is going to be of type, I've actually got one called solvent, so I'll use that. I'll speak about the ranges in a second because I'm going to show you the manual input and the database input. So the formula that you need, this will be more apparent once I've brought it in from the database. So let's start by, you saw for the brucine that I entered those values manually, and I can add additional ranges if I need to. So let's try importing the ranges from the database. It's in that database. Okay, so there you go. It's actually read the molecular weight as well, which is nice. And it's brought in two ranges here. Okay. So that's a lot easier than entering it manually, obviously. And what we need to do now is to adjust the formula to reflect the fact that we've got two ranges. So I need to take the average of these. So I'm going to take that plus I2 divided by NN2, all of that divided by 2. Okay, that's the average of those two normalized integral regions. Okay, so you can see in here that I've got I1 and I2, NN1, NN2. That's what I'm using in the formula. I can check it to make sure that I got all the brackets right. That's fine. It's an easy one. And that's all I need. So that's basically representing the area of, or the concentration, if you like, of the ether. Don't forget to add it. There we go. Okay, so this particular expression here, number 2, is going to calculate something that's related to the concentration of brucine. This expression is going to calculate something related to the expression of ether, and we need to use these now to determine the mole percent. So, oopsie. So, mole percent, this has no meaning. Ranges are not required because I'm going to just be using the values that are previously determined. So the molecular weight's not relevant. This is whatever. And here it might be useful to put valid ranges. So I might say that I'm happy with something from 0 to 10 as a mole percentage. And now I have to put in a sensible equation for that. Okay, so you see now that under the compounds I've got the result of calculating the concentration of brucine and ether. So the mole percentage is 100 because it's a percentage, 100 times, so it's going to be C Yep. Okay, let's check that. It's happy. And we click on OK. And we add it to the mix here. So at this stage we've got everything we need. We've got a little experiment. We've worked out the concentration of the brucine, the ether, and then we've divided the two to work out the mole percent. If I wanted to work out the weight percent, then I could include references to the molecular weights of those compounds. Okay, so I click OK, and that gets added. Click OK again. It gets added to the list here. So now there should be our new one. It's the one we just created. And all I have to do is to run it now. This is ready to go. So undock that and analyze. So there we go. I don't think I ran the correct one. Apologies. I think it's that. So this is the problem of using silly names. There we go. Okay, so smart cuts. This shows us the two ether peaks, the brucine peak, and that's the mole ratio that we calculated. Okay, that's our first example. We've created an experiment from scratch. So the second example really is to show you a little bit about, so we created this simple mold experiment, mold percent experiment. I showed you how to use the DB, the database for simpler ppm range insertion, and now I'm going to show you a simple PPR demo. Okay, so we actually used the same data for this demo. I'm going to remove the peaks from here, delete all the peaks. I'm going to clear the table, come back here, and I'm going to use this experiment, and I'm just going to show you how that works. Okay, so it's very much similar to what I did previously, except for the fact that if you look at this is it's very strange. These names have gotten mixed up a bit. Okay, so you can see here for the ether that I've got ranges, and importantly in this case, because I'm using peak pattern recognition, I've got a file that's specified in this column over here. Okay, so this refers to a file of ether, the spectrum of ether. Everything else is pretty much as I did in the previous example. I'm just looking for the components differently. Okay, so I can run that, and what you see in the alerts is that it tells me that it's used the PPR to find the particular multiplets that I want to find. So it's found the ether triplet, the ether quartet, those two, and this is the confidence or the probability that it's found it correctly. So it's happy with that. This is, as I say, a fairly trivial example. It is a trivial example, but I hope you can see that this would be more relevant if you had spectra that had overlapping lines and you'd like to find a particular multiplet or peak pattern within those overlapping lines. So as I said earlier, the peak pattern recognition is in its beta phase at the moment. It's not something that we stand by 100%, but you're very welcome to try that and see if it works for you. And we'll certainly, of course, be adding more effort to make it more robust as time goes by. Okay, so that's that. Now, I wanted to also speak about maths in SMA formulae. That's quite easy to do. So we'll go to a different spectrum. It's a spectrum that I showed in the previous webinar. So clear the table. And in this case, I go for this particular experiment. I'm going to read the parameters from the title file here. So read the parameters, going to put the important information in here. So what are we doing in this case? Let's go to the edit experiment and see what's happening. Okay, so remember this is a purity determination. So I've got my certified reference material, which is dimethyl sulfone, specified over here. I've got two peaks that I'm using from the catechin, this particular range over here, and the second one, which is a second methionine or methylene pair. And the equation that I've got in the formula editor is the classic equation for purity determination. There's nothing fancy there. If you look in the previous slides, that's pretty much what I've got there. Okay, so I've determined the purity independently for one particular multiplet, the one here at about just less than 5 ppm. I've independently determined the purity for a second multiplet, this one at about 4.5 ppm. And what I want to do now is to look at the averages and so on. So if I look at the average, this is a very simple value here. This is the Catchin 1, so this is the purity as determined by multiple number 1 and added to the purity determined number 2 and divided by 2 because there's 2 of them. Okay, so that's just determining the average, and determining the RSD would be a more complicated equation that uses the values that you saw in those maths functions, and it looks a bit nasty, but it's not that bad. I don't have it in this experiment as it happens, but I can certainly describe to you how to set those up. So that's okay, and we can analyze with that, and you'll see the results. Hold on a sec. Okay, that's always embarrassing when it fails. I don't know why that failed. Okay, I apologize for that. I'll fix that. Okay. Right, the last thing I wanted to show you was batch purity. That's very simply done. So under SMA automation, we have the listener capability, which is the real-time monitoring, and we have the batch. Now what I've done for the batch is to copy a single file 4 times, and I'll show you that file. And what I wanted to show you is that within the title you do need to specify the experiment. So in this case is that, and the reference concentration I need to know as well for this particular analysis. So I have this file repeated 4 times in a particular directory, and so we can analyze it in this way. So you have to specify the current SMA library over here, and then you specify the base directory. So this is the directory where the particular files are hiding, or located, I should say. So I select that folder, and this is a mask that tells me how to get at those files, so star.mnova files, and if I click on the little view button here, it shows them to me. Yeah, so I've got the 4 files there. Okay, I can specify processing template file, MNP file if I wish, and I need to tell it where to put the data, so I'm putting them all in the results folder over here, and every time I do an analysis a new directory is created. So these are ones that I clearly did earlier, so we click on OK and it all starts working. That's it, they're all done. So let's go to the folder and see what we have. So we have a new directory. Okay, there's a new one here. And you can see for each of the 4 spectra we've got a little results table, which will show up in your web browser, as well as the file itself. So you could open that in Mnova and play with it. This is repeated for all 4 of them, and the log file is written too. This doesn't have anything in it. If there were alerts, they would be shown in here. That's all there is to showing you the batch. And I said previously that it's a pretty boring demo, and that's all there is to it. There's not a lot to see really. It just works silently and does everything for you. Okay. That's that. So, coming soon to version 1.1, we have some capability that allows you to look at the mixture spectrum together with the components in the database. So if you believe there are particular components that are present in the mixture, you can view those together with the mixture spectrum and superimpose them if you like, and move them around a little bit horizontally and vertically. We've got a capability that allows for automatic equation writing. So this is going to greatly simplify the whole process of writing those equations. Obviously, you might have found those a bit daunting, so I didn't show you how to write the equation for the residual standard error, but that's on a button now. So you simply press that button and the whole equation gets popped in for you, and you don't have to worry about all the syntax and whether you've got the right number of brackets and so on and so forth. So there's automatic grouping of multiple ranges. So you remember that for the catechin I had one region and a second region, and these can be automatically grouped rather than considering them to be individual compounds. So this greatly facilitates things, and it makes things more tidy, and it also facilitates the statistics, because you can work out the average and the standard deviation quite easily for those particular components of ranges of a component. And you can select the ranges that will be used in the analysis after the analysis has occurred. So that will be coming up in the next few months. Hopefully this will be ready for ENC. Okay, so we're at the end of the road here. I've got the same conclusion slide that I used for the first webinar. I hope I've shown you that SMA is a powerful, flexible tool for mixed analysis using targeted methods. You've got the full user control of every aspect of the analysis, whether it's the writing of the equations and the setup of the experiment, or whether it's the actual way in which that's executed. It's a powerful experiment design capability. So you've got ability to, for example, address different spectra that were acquired on the same sample. And the workflow ensures confidence in a correct analysis. These are using, referring here to the alerts and how you use those to then point to areas where you might have problems in the detection, and then you can go in and fix those. And it has this simple operation interactively, or if you're working in a higher throughput mode, then it has the batch or real-time operation as well. And with that, I'm all done, and I thank you very much indeed for your time and attention.